Okay, the extra practice problems for Chapter 9. Number 1, barium sulfate is insoluble in water. If a solution of barium nitrate and water is mixed with a solution of sodium sulfate and water, what reaction will occur? And so you have to be able to look at the information he's given us here and come up with the problem. So we're told that barium sulfate is insoluble in water, which means it's going to be a solid. And we're told that a solution of barium nitrate and water is mixed with a solution of sodium sulfate and water. So the barium nitrate, first off, you're going to do the barium. The barium is in group 2. You would look for that, so it's a +2 metal. And nitrate you have memorized as NO3 minus 1. And so this gets the 1, this gets the 2. And we are told that that is in water, so it is aqueous. The next one, it says, is sodium sulfate. Sodium is a group 1 metal, and sulfate is -2. And so this gets the 2, and the sulfate gets the 1. Once again, it is also in water, so it is aqueous. And it tells us that barium sulfate is insoluble in water. So we're going to go barium, which is +2. And sulfate, which is -2, so that's a 1-to-1 relationship. So we're just going to ditch the numbers there. We're told that is a solid. And so what's left is sodium, which is a +1, and nitrate, which is a -1. So that's a 1-to-1 relationship. And we're not told that's a precipitant or a solid, so we're going to assume that that is aqueous. Okay, so now we have to go about balancing this. And so I always start from left to right. It doesn't always work out really well, but I start from left to right. So we have 1 barium, 1 barium. We have 1 sulfate, 1 sulfate. We have 2 sodiums. So I'm going to come down here and put a 2 here. And we have 2 nitrates. So we only made 1 change, but let's check it. So we have 1 barium, 1 barium, 2 nitrates, 2 nitrates, 2 sodiums, 2 sodiums, 1 sulfate, 1 sulfate. So we are balanced. So that is what this should look like. Remember that if we're not told that it is a solid, then you're going to assume that it's aqueous. We were told that this one is a solid, so that's why it got the solid. A solution is made by dissolving 15 grams of silver nitrate in enough water to make 125 mils of solution. What is the concentration in molarity, or moles per liter? So we are given 15.0 grams of silver nitrate. And so let's find out how many moles that is, because we know we're going to have that in moles per liter. So I'm going to go like this, and I've got grams of silver nitrate, because that's what's here, so it has to go here. And I want to go to moles of silver nitrate. 1 mole of this, we're going to add this up, and when we add it up, it is 169.88. And all I did was went to my chart, found what silver weighed, added it to what nitrogen weighed, and then 3 times what, this is going to be 48, isn't it? What oxygen weighs, put it together, and that is where we got that number. So this answer has to be in 3 significant figures, so it's 0.0883. This will cancel, and we'll be left with moles of silver nitrate. Now, once we have the moles of silver nitrate, we need to divide it by the number of liters, and we're told that we have 125.0 milliliters, and I'm going to show you this once, and then I'm not going to do it again. And 1 liter, there's 1,000 mils. So what we're going to do is move this decimal place back by 3. So we're going to take this and divide it by 1250 liters. Please notice there are 4 significant figures here, therefore you have to have 4 significant figures there. And so when you do that, your answer has to be in 3 significant figures. And so it's going to be 0.706 molar, because that means moles per liter. That's what that means. So I just wanted you to see that. Number 3, you want to make 500 mils of a 3.0 molar solution of potassium chloride. How many grams of potassium chloride will you need? Very practical question. And so we know that the molarity equals moles per liter. And we are told that this is 3.0 molar. Okay, we want to know how many grams, so we're looking to get up here, aren't we? Well, we need, if we have 500 mils, so why don't we plug this all in? We know that 3.0 molar equals the number of moles divided by the number of liters, which in this case, 500 mils would be 0.50000 liters. So when we multiply this by this, we know that we have 1.5 moles of potassium chloride. And the question was, how many grams would that be? Well, we can very easily go from the moles of this to the grams of this, can't we? So in every 1 mole of potassium chloride, there is 74.55 grams. I just added those two up. And so 1.5 times 74.55. We have two significant figures. What comes out of my calculator is 111. I'm just going to show you 111.8 blah, 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 blah grams. But look at this. We need two significant figures. This number in two significant figures would be 110. So the answer would be 110, not this, because that has too many significant figures. So make sure your answer is this. Number 4, a chemist wants to make Bi2S3, I think it's bismuth sulfate, according to the following reaction. If the student uses 67.1 mils of 2.9 molar solution of potassium sulfate and an excess of bismuth nitrate, how many grams of bismuth sulfate will be formed? Okay, so the best way to do this, and what I told you in class, is to set up your equation with your information. The best way to do these problems is to put your equation, your balanced chemical equation out, and then write your information into it. The student uses 67.1 mils of 2.9 molar potassium sulfate. So right here, we're going to have 2.9 molar, and we're going to use 67.1 mils. I know I'm going to need that in liters, so I'm going to go ahead and convert that by moving the decimal place back by 3. And so that's the number of liters that I have of that. And we have excess of this, so we're going to calculate from here how many grams of this are formed. There's our equation with our information in it, what we're given and where we're trying to get to. You always start from where there's no question mark and drive to where there is. You know, the only way from here to here is through the mole bridge or the mole tunnel, however you want to look at it. And moles is hidden right there, isn't it? Because molarity is moles per liter, correct? So that's where I'm going to start. I've got 2.9 moles per liter of potassium sulfate. And I'm going to go ahead, and to get that to moles, I have to get rid of the liters, don't I? Well, I'm given the liters, 0.0671 liters. And so that's going to give me, in two significant figures, 0.19 moles of potassium sulfate. Now I'm to the moles of this. I use this and this to get to the moles. Now I can go from the moles of this to the moles of this. So I'm going to do that. I'm just going to, for simplicity's sake, erase that, and I'm going to keep going. I have moles of potassium sulfate, and I'm trying to get to the moles of bismuth sulfate. For every 1 mole of this, there's 3 moles of this. And so we go 0.19 divided by 3 equals, okay, two significant figures, 0.063 moles of bismuth sulfate. And I want to know the grams. So I'm just going to times line it. This goes here. Grams goes up here. 1 mole of this, you're going to add up the bismuth sulfate 514.14. That's a heavy dude, isn't it? We have two significant figures, so our answer has to be in two significant figures. So this way, you can see how when you have a particular solution, that if you know the molarity of the solution and how much you're going to use, you can calculate the grams of what you're going to produce, and vice versa. You can go back and forth with this. Number 5. A chemist wants to make 50 grams of hydrogen gas following the following reaction. If she has an excess of magnesium, what volume of a 4.12 molar solution of HCl will she need to use? Okay, we have excess magnesium, so we're not calculating from that. We have 4.12 molar hydrochloric acid, and want to make 50 grams. We want to make 50 grams of hydrogen gas. What volume, so this is the question mark here, is the liters of that. What volume are we going to need? Okay, so now we have our question mark. We have our information written in. Notice we have a question mark over here, so we have to start here because we don't have a question mark here. And I know I'm going to have to go through the moles, so I'm going to take this to the moles. So we go 50 grams of H2 times line, grams of H2, moles of H2, it's ugly 2, 1, and this is 2.02. Three significant figures, 24.8, because I have in my calculator 24.75, so 24.8 moles of H2. Now I'm going to ditch this because I want to go from here to here. I want to get from over here to over here. So I'm going to go times line, moles of H2 to moles of HCl, because that's taking me where my question mark is. I have a 2 in front of this. I have a 1 in front of that, the invisible 1. So 24.8 times 2 equals 49.6 moles of HCl. Okay, so now I have the moles of HCl. I'm going to bring that back over here. And my question is, how many liters? Okay, so to do that, I'm going to go times line, and my molarity, this is my shortcut that I showed you in class. You know whatever's here, here has to go here. And we're trying to get to liters, aren't we? Right? And we know this is moles per liter, so I'm going to flip it, and I'm going to go 4.12 moles per liter. There's my molarity, 4.12 moles per liter. And so 49.6 divided by 4.12 equals, and that is going to be in three significant figures, 12. I can do this. 12.0, and this leaves, and I'm left with liters. So there's your answer, is 12.0 liters of solution. So once again, you start where there's no question mark, you get to your moles, you go from moles to moles. It's the only way you can get from one place to another in the equation. Then once you had the moles here, this is where it might have gotten a little tricky, because remember, moles per liter is what molarity is. So we just literally did a times line and flipped the whole thing. And you saw in the book why we can do that. And so that gave us our liters. Number 6, if you make a solution by mixing 40.3 grams of magnesium chloride with 750 grams of water, what is the molality of the solution? Well, remember, molality equals the moles of solute divided by the kilograms of solvent. And so knowing that, we have to find the moles of the solute. Well, we're given 40.3 grams of magnesium chloride. And so we're going to convert that to the moles. And every 1 mole, we add this up, and it's 95.21. So we go 40.3 divided by 95.21 equals 0.3 significant figures because of over here. This has 4. 423 moles of magnesium chloride. So we've got our first number, 0.423 moles of solute divided by, now we need the kilograms of solvent, and we're told that we have 750 grams of water. So we know that we moved that decimal place back 3 because we know that there's 1,000 grams to every 1 kilogram. So that's going to be 0.7500 kilograms of water. So we're going to go 0.7500 kilograms. And so our answer has to be in 3 significant figures, and it's going to be 0.564 molal. 3 significant figures. Number 7, a chemist makes a 1.76 molal solution by mixing sodium sulfate with 150 grams of water. How many grams of sodium sulfate were used? Once again, molality equals the moles of solute divided by the kilograms of solvent. So we know that we have a 1.76 molal solution, and we know how much water was used, which is 150 grams, so we're going to move our decimal place back by 3. So it's that many kilograms of water, and that will tell us the moles of sodium sulfate. So we go ahead and multiply those 2 numbers. That gives me 0.264 moles of sodium sulfate. Now, we wanted the answer in grams, didn't we? That's what they asked for. So we're going to take our number of moles, and we're going to go moles of sodium sulfate, grams of sodium sulfate. In 1 mole, there are 78.04 grams. We have 3 significant figures. My answer is 20.6 grams. Yep, 20.6 grams, and I can't really fit it here, so I'm going to write it down here, of sodium sulfate. Shame on me, I left out the subscripts. Sodium sulfate. There you go. So you use this, you plug in what you've got to find the moles. Once you have the moles, you can figure out the grams. Number 8, solutions are made from water and the following solutes. We have sodium chloride, strontium chloride, barium nitrate, ammonium phosphate, C2H6O, and sodium sulfate. If the molalities of the solutions are all the same, which will have the lowest freezing point? Well, remember, because the change in temperature equals -I K molality, and we're asked which one will have the lowest freezing point. They all have the same molality, so this is what's going to make the difference. The one with the largest I will actually have the lowest freezing point. Now, sodium chloride is 2 ions, sodium and chloride, so that I would be 2. For strontium chloride, there's 1, 2, 3 here, and so I would be 3. And if you don't see that, you've got a sodium and a chloride ion. Here you've got a strontium and 2 chloride ions. There's your 3. Barium nitrate, that would have 3 ions, barium, and 2 nitrate ions. So that I would be 3. Ammonium phosphate, well, there's 3 of these and 1 of these, so that I would be 4. The next one is covalent, so its I is 1. And then the last one is sodium sulfate. There's only 3 there. There's 2 of these and 1 of these, so this I is 3. So who has the highest I? This one does. And this would give us the lowest freezing point because it's got the highest I. So that one is the one that you would choose. Number 9. What is the freezing point of a solution made by mixing 150 grams of potassium with 550 grams of water? So we want the freezing point. The change in temperature equals negative I Kf. There we go. And we want to know the freezing point. So let's find, we're first given 150 grams of potassium chloride. So we have 150.0 grams of potassium chloride. And with 550 grams of water. Well, this is what's going to help us with, that's the solute. And that, so we need to remember the molality is the moles of solute, which is this, divided by the kilograms of solvent, which is the water. So we move the decimal place back by 3. And this gives us the kilograms of water. Okay, so we need this. So we're going to go like this, grams of potassium chloride, moles of potassium chloride. We know in 1 mole of this, there's 74.55 grams of that. And so that's going to give me, in 4 significant figures, 2.012 moles of potassium chloride. So now that I have that, I can go 2.012 moles of potassium chloride, and this is kilograms of water. And so that's going to give us our molality. I have 4 significant figures, so I've got 3.658, and that is the molality. So now I can come up here. This is, I is going to be 1, 2, because there's 2 ions that this will break into. So negative 2. Kf is given to us as 1.86 degrees Celsius per mole. And then we calculated the molality as 3.658 mole. That gives me a negative 13. Got 3 significant figures here. This one is an infinite number of significant figures, so I have to have 3 significant figures in my answer. These will cancel, and I'll be left with degrees Celsius. And because we're working with water, that's actually the new freezing point, is negative 13.16. Because remember, then you take the freezing point, which in this case is water, subtract the 13.6 degrees Celsius from it, and that would give you your negative 13.6 degrees Celsius. If you were starting with some other solvent, you would have, and it had a different freezing point, you would start with that freezing point and subtract this from it to get your answer. What is the boiling point of a solution, of the solution in number 9? The boiling point is going to be IKB molality. The molality we figured out was this many moles divided by this many kilograms of water. So here the I is still 2. The KB is 0.512 degrees Celsius per mole. And the molality we calculated as 3.658 mole. So we have 3 significant figures limiting us. My answer, the change in temperature, is 3.745. So I'm going to say 3.75 degrees Celsius because this will cancel. Now you're not done yet. All you found is the change. And we are using water as the solvent. So you're going to say 100 degrees Celsius plus the boiling point elevation is going to give you, plus the boiling point elevation is going to give you 103.75 degrees Celsius. So that is your answer. Don't stop here on your test. It won't be done. That's not what you were asked for. Number 11, the boiling point of ethanol is 78.37 degrees Celsius if the boiling point of the solution of water and ethanol is 80.56. What is the molality of the solution? Okay, well here we're doing boiling point, so we're going to go the change in temperature equals IKBM. And we are trying to find the molality. So I'm going to go ahead and solve for it. Delta T over IKB. Now, we are told that the starting, remember, the change in temperature equals the final minus the initial. And the final is 80.56 degrees Celsius minus the initial, which is 78.37 degrees Celsius. That's a 7. And so 2.19 degrees Celsius. So that gives me this. 2.19 degrees Celsius. I just took the final minus the initial, and that gave me my change. Remember, we're adding or subtracting, so you have to go to the least precise, which is to the hundredths place. Okay, divided by I. Well, now we figure out I by what we're working with, and we are working with the boiling point of ethanol and water. Ethanol is not an ionic compound, so I is going to be 1. And then the Kb we're given as 1.07 degrees Celsius per mole. And so that's going to give us, in 3 significant figures, I got 2.046, so I'm going to go 2.05. These are left, so I'm left with molality. So it's 2.05. So go ahead and just put in what you've got and then go find what you need and then let your units help you to figure it out. Pray hard. Have a Jesus-filled week.